Hello? Oh, there we go. So I'll get started here. I guess I'll be my own cameraman for the moment. So generally speaking, as I'm lecturing, if you got questions, you just gotta ask them, all right? So I'm just trying to get my course notes up here so that I don't forget something. So let's start with just coordinates, all right? So we can talk about points and vectors, all right? So those are so first of all, if I'm just talking about the plane, you guys know this pretty well. We have x, we have y, right? If I pick a point here, then typically you could say something like that point is at x comma y, let's say, right? Nothing too surprising. Of course, when I think about a point, I think about just, a point, right? But you can also think about this in terms of a directed line segment from the origin, right? That's called a vector. So to picture the vector, goes like this. And so I would, let's see here. Think of that as the vector p. And so the vector is just the directed line segment. So I use this Langle-Wrangle bracket to indicate directed line segment, all right, vector. Now, as a point of, annoyance, you can identify these two things, right? Because if you have a point, I can tell you what the point is if I give you the vector, right? Like, if I tell you you're going this much over and this much up from the origin, that uniquely specifies the point and vice versa, right? Like, if I give you the point, you can find the vector. Now, the vector, though, unlike the point, you can think of in terms of other vectors, because vectors allow a natural notion of addition. So like vector addition, let's talk about that. Geometrically, you can think about it tip to tail. So if I have, this is vector A, and this is vector B, right? Notice I've drawn the tip to tail, right? Where A ends, B starts, right? Every vector you could define by an initial point and a terminal point, right? You can think about vectors as directed line segments, if you like, all right? But geometrically, what is A plus B? What's it look like? So A plus B is down here. So this is tip-to-tail vector addition. So if you think about this vector in the plane, x comma y, right? We can write it actually as a sum of vectors. And in particular, we can break this vector into two pieces. Oops, well, it's not. I already got one of those. So let's see here. I've got this piece down here, right, which it's the vector x comma 0. And then I've got this vertical vector over here, which would be 0 comma y. So x comma 0, because it's not going in the vertical direction at all, right? It's just going horizontally in the x, that much in the x direction. This is going that much in the y direction, like that. So with the understanding that we identify points in vectors, we can write the following, right? The point we can identify with the vector which points from the line from the origin like that. And you can see from this picture, using the geometrically defined tip-to-tail vector addition, that that's equal to x comma 0 plus 0 comma y, let's say, right? And then there's another thing we can talk about, right? We can talk about so-called scalar multiplication. So scalar multiplication, if I have, let's say, vector A like this, right? What happens if I do A plus A? What would that be? Like do another one of them, right? So this altogether would be what? 2A, which, I mean, if there's any justice, it should certainly be equal to A plus A, right? But 2A is a scalar multiple of A, right? A scalar multiple of a vector is in the same direction as the vector. So using that idea down here, we can rewrite this as like x times 1, 0 plus y times 0, 1. All right. And you notice that like you can do this same argument for any point in the plane. All right, I've drawn a point in the first quadrant, but you could just as well make this calculation anywhere. So let me just tell you, these two vectors that I just wrote here, 0, 1, and 1, 0, these are special vectors. They're the so-called unit vectors. If I was to try to draw them up here, looks something like, I don't know, it depends on how long this is. Let's suppose this is like 2 units long, all right? Then this would be the, well, I'll call it x hat, all right? This is what's called, I call x hat. Now other calculus books sometimes call, it's also known as I hat, sometimes bold-faced I in like calculus books, right? This is the unit vector of length 1 that points in the x direction. And on the other hand, this one, if you look at just a 1 unit long vector there, is called y hat. Y hat's this guy. In usual calculus books and a lot of engineering things, they use j hat. I prefer you use x hat and y hat. Yeah. But you should understand they're the same because you'd like to be able to read other things. Listen, so if you're like me and you're mathematically minded, and about 30% of you are, well, 30% of you are like math majors or something like that, right? So you'd like a definition, right? And so I've given you sort of a geometric definition of vector addition, vector multiplication, but we can do better, all right? So let's talk about Rn. So what is Rn? Actually, I probably shouldn't do Rn. That's probably a little bit too far. Have I been over here the whole time? Or was I over there? Somebody move this camera? Somebody move the camera. Well, hopefully somebody moved the camera. Otherwise, I've been off camera. All right. Anyway, so Rn. So this whole arena here, right, is R2. All right, Rn, what's Rn? Rn is the set of like x1, x2, xn, such that x1 through xn are real numbers. So this thing here means element of, if you didn't know already. R, this funny looking R is the set of real numbers. Hopefully that's not news to you. You could also write it as minus infinity to infinity if you like, using interval notation, right? But this is so-called n-dimensional, usually Euclidean space. So in n-dimensional Euclidean space, we can define vector addition and scalar multiplication pretty simply, all right? Like here's how you do it. And in fact, we really want to define it for vectors more than we do for points. So let me just think of this in terms of vectors here. So if I have, let's see here. If I have like vector v plus vector w, and I want to tell you what's the, like the jth component of it, or if I have c times vector v, I want to tell you what the jth component of it is, what would those be? So let's see here. Over here, just to go back to my initial one, if this was A1, A2, and this was B1, B2, then this would have been A1 plus B1, comma A2 plus B2. All right. And we could have derived that from breaking each of the vectors A and B into little horizontal and vertical like steps, and then adding the horizontal steps together and adding the vertical steps together, under the assumption it doesn't matter which ones you add first or last, right? It's commutative. So with that idea in mind, you can kind of see what the general definition should be, right? Like to find the jth component of v plus w, you just take the jth component of v plus the jth component of w. To find the scalar multiplication of c times v, you just do c times vj. And this is for j equals to 1 to n. All right. Now, I try not to stay in n dimensions in this course too much because we're mostly interested in 2 and 3 dimensions, all right? But there are places in science and engineering where, despite the fact that I personally can't can you visualize 4 dimensions? I'm not, iffy. Yeah, I can't. My brother had a postdoc at Rutgers, and he went to a talk by one of these guys who's a popularizer of string theory, and the talk he was giving to at the Institute for Advanced Study, in that talk there was like 20 people there, some of them really the leading theoretical physicists of our time, many of whom's whole life work has been in 10 or more dimensions, right? They've written dozens and dozens of papers in like 10 dimensions, 26 dimensions, right? Deep technical papers. And he asked them, can any of you visualize 4 dimensions? What about 5? And they're all like, no. Like, how do you write papers if you can't even picture it, right? Well, the answer is the way we think about higher dimensions is through equations and algebra, right? We can't directly visualize things. Now, you have a great benefit in 3 dimensions. You can directly visualize things, right? But we also need to learn how to understand those things in terms of concrete algebra. And that's where vectors start really helping, all right? They give us an algebraic way of understanding things that we can't really quite picture. All right, anyway. So let's see here, example 1. Let me just be a little bit more concrete here. If I have vector v is equal to 1, 2, 3, and if I have vector w is equal to 0, 1, minus 2, all right, then let's calculate v plus w. So how do you add vectors? You add components, all right? So 1 plus 0, 1. 2 plus 1, 3, right? 3 plus minus 2, 1, right? So there you go. That's v plus w. Now, let me try to draw a picture of what we just did. Let's try to visualize that. So here's my usual picture. This is the x direction. This is the y direction. This is the z direction. All right. This is a so-called right-hand coordinate system. More on that from a technical perspective as the week goes on. All right, so if I'm so foolish as to try to picture v and w, which I just made up with reckless abandon to my visualization, how do you picture W? Well, it's 0, 1, right? So that means it's going 0 in the x. It goes 1 over in the y, and it goes 2 down in the z. So it's like in the plane that's spanned by the z-axis and the w-axis, if you can understand my meaning. So 1 over, 2 down. So something like this is my w, right? Where's v? 1, 2, 3, right? So it goes 1 over in the x, 2 over in the y, 3 up in the z. So it's something like this. Of course, do these pictures do it justice? Of course not, right? Now, look, this v I can write as x hat plus 2y hat plus 3z hat. You should understand, we use the notation x hat, y hat in different ways. In 2 dimensions, it's a 2-dimensional vector. If we're dealing with a 3-dimensional problem, we think of x hat and y hat as 3-dimensional vectors. So what do you think this x hat, y hat are in this context? What can you tell me their formulas? You're like, it's your lecture, you define them, right? But yeah.
1, 0, 0, 0, 1, 0, 2, 0.
Now, so as people seem to be able to answer questions which I haven't really defined in this class, if that disturbs you as a newcomer, there's a reason for this. It's because these people have suffered a semester of my physics course. And so they already know everything we're talking about backwards and forwards and upside down, because otherwise they would have failed my physics course. So do not be intimidated. I'm just saying, if you're new, just focus on the homework. If you do the homework, you'll be okay. Although much of the homework you won't be able to do after today, because we're just covering the start of it today. Anyway, so enough blathering. These are the unit vectors. Now, if I try to picture that, what's that like? See, if I try to do it in this picture, it's not going to go well. All right? But you see, you could break. Oh, fine, I'll try. This is ill-advised. But so x hat, you go like one of these, right? And then you go like a y hat and a y hat, 2 y hat over, right? And then you go 1, 2, 3 z hats up. And so you can build v from vector addition, tip-to-tail vector addition from the origin, using these so-called unit vectors, x hat, y hat, z hat. And I could do the same for w, but I've cluttered the picture enough. Now, where is v plus w in this picture? That's where it gets even uglier. Now I'm really going to mess up my picture. So v plus w is 1, 3, 1, right? So how do you think about that? Do you start at the origin? Well, yeah, I mean, you should. So 1, then 3 over, and then 1 up. So it's like here-ish would be v plus w. Now, can you, oh, goodness gracious, that is not a plus, is it? Yeah, don't do that. Plus and times are very different here. Putting a times between vectors is something much uglier, which we'll get to. So-called cross product. All right, so if you can see it, if we take v and then we add w to it, I can't see it, but if we think, well, I mean, maybe you can, I don't know. You basically think about taking this w and moving it up here. I'll just make it dotted like that. This would be the w. So you got v plus w. At this point, I think I've made the picture so horrible that no one can follow it, right? So let me stop. Anyway. If you're confused, my apologies. It's probably my fault. Let us go on, though. Okay, so let's talk about vector from point P to point Q. All right, so I should talk about that. There's not much to say here. If I have point P, I have point Q, I can talk about this vector here from P to Q, which we call PQ. Right? What's the formula for the vector from P to Q?
Q minus P.
Q minus P. Very good. Yeah. So Oh. Yeah, better.
Is that a shirt?
Yes. It's my eraser shirt. So example 2.
Oh, I was music again.
Oh yeah. Am I in? Can you see? Am I? Okay, cool. So let's think about. Let me make my points easier to understand this time. How about like 3, 0, 0, and q equals to, oh, I don't know, 0, 1, and 2. All right. So let me draw another picture. Let's visualize these with my suspect three-dimensional picture, x. Of course, this is a perspective. I mean, so 3, 0, 0 would be something like here, right? And 0, 1, 0 would 0, 1, 2 rather would be where? So it's 0 for x, right? So you go 1 over for y and 2 up for z. So it's something like here, right? So if we wanted to visualize the line segment PQ, right? That is this character here, right? And can you tell me the formula for it? Like you guys told me, Q minus P, which when we do the math here, what's that give us? Negative 3, 1, 2. Very good. So my question, I guess my next question to you would be, where would you say PQ is based? Like, where are we thinking of that vector as emanating from? You say P. I would say that my question is a little bit ambiguous because of the usual customs of this course. But yeah, I think the natural thing to say is that this vector is based, well, as I have it drawn right now, right? I have, illustrated it. PQ is based at P, right? That's its P is its initial point. Q is its terminal point. One of the first things I should mention about vectors as we think about them in Calculus 3 is we allow ourselves to move them around, all right? Like I can so-called parallel translate this vector other places and I still think of it as the same vector. Okay, so, but you notice, right? I don't know if you can see this or not. If I was to, oh no, I'm not even try it. I could try to explain to you that this is also equal to like the vector Q minus the vector P. That is a reasonable thing to think about. What does the vector minus Q look like? Let's not invest class time on this. It will go badly. The picture is not going to help. But we can think of this as like a difference of vectors, if you like. Okay, anyway. My more interesting question to you is, what's the distance between these points? Right? Let's think about that question. What's the distance between point P and point Q? And to answer that, well, there'd be an easy answer to that. It's just the length of the vector that connects them, right? Like if I knew the length of the vector PQ, then I could tell you the distance from P to Q. How do we calculate the length of a vector, though? What's the definition of that? I'll give you the definition. Length of A, and I'll give you a three-dimensional definition because that's perhaps something new. Length of A1, A2, A3. Oh well, I tried. Thank you. for the assist. Let's see here. So we have a notation which is the length of A, which we also call A. It's the square root of A1 squared plus A2 squared plus A3 squared. All right? This is the length or magnitude of the vector. Notice the notation. You have to draw the vector if it's a vector, all right, in this course. The vector letter without the vector sign is a number, a scalar. It's the length of the vector, all right? This makes total sense if you just picture it in 3 dimensions, right? If A looks like this, right, I can break it up into 3 pieces, right? I can break it up into A1, x hat, A2, y hat, and A3, z hat. What's the length of they're all right triangles, right? So like in the plane, in the xy plane down here, we've got this right triangle, right? What's the length right here? It's the square root of A1 squared plus A2 squared, right? And then if you look at the vertical triangle there, what's the length of that? I mean, what's going on here? We got this vertical triangle, right? It has this as the length of the base leg. The vertical leg has length, well, absolute value of A3, technically speaking, but you can see that the length of this guy right here is what? It's the square root of A1 squared plus A2 squared plus A3 squared, right? Which is exactly that. So that's why this formula makes sense, is you can view it in terms of the 2-dimensional distance formula you already know, right? The Pythagorean theorem, if you like, right? So then I come back to my question. For example 2, what's the distance between P and Q? How do you calculate it? So definition, the distance from point P to point Q is equal to the magnitude of, the magnitude of the PQ vector, basically. It's the length of, which of course we could write more specifically as the length of Q minus P, like that's actually the mechanics of how we do it. Continuing example 2, for my example, what's the distance from P to Q? It's what? The square root of what? Well, right here, right? The square root of, it's the length of the vector minus 3, 1, 2. To calculate the length of a 3-dimensional vector, we take the square root of the sums of the squares. You can ignore the sign, right, in this calculation, because minus 3 just gets squared to 9. And so the length between these points, distance between these points is just what? It's 10 plus 1 plus, what did you say? Square root of 14. Sounds about right. Square root of 14 what? See, we as a matter of custom in Calculus 3, we leave it open to interpretation, all right? You could think in meters, you can think in feet. If you got one of these, let's see if I got my toy. Did I bring my toys? Oh, here. Check it out. So if you got a measuring device, I can tell you it's 356.4 inches to over there. 214.4 inches. See, that just grieves my heart. There's a way to change it to meters. Oh well, I may not burn Calculus 3 time on that. My point is, to actually set up a coordinate system, you need some kind of measuring device, right? And it's not just length and distance that you need to understand. You also need to understand a sense of like direction, right? So you need something more like this. Hey, come on. Something like this, right? Something that will tell you not just distance, but angle between, you need to be able to set up perpendicular lines. This is the other thing we have to grapple with doing. I've been remodeling my basement. I got some toys, to set up vectors and distances. Now, One final thing for today. So we don't yet have the tools to calculate angles between vectors. I've showed you how to add them. Hopefully I've given you some sense of how to think of them geometrically. If you read the notes, there's more in the notes than I've said here. Okay, I can never say everything I say in the notes. I just try to hit the high points and give you a flavor. But the other important idea that will solve a bunch of homework problems, test problems, other things, is the concept of a unit vector, right? So here, the vector A, we could also write as the magnitude of A times A hat. So this is magnitude or length, and this is direction. Now what's the formula? The direction we can give by a unit vector. Now here, I have worked myself into a corner of sorts. So I'll go over here. I would point out, while we can't visualize n dimensions, the formulas I just erased are just as easy as the ones we've been using in 2 or 3 dimensions. It's really not harder. Anyway, so A hat here is a notation for 1 over A times A vector. So this is the definition. My third and final example for the day is if I have A equal to, say, 1, 2, 2, then the length of A is the square root of 1 plus 4 plus 4, which is the square root of 9, which of course is 3. And then A hat is 1 over A times A vector, which means 1 over 3 times 1, 2, 2. That, my friends, is the vector 1, 3, 2, 3, 2, 3, if you want me to break it into that kind of format. And that's a unit vector. What is a unit vector? Yeah.
Magnitude of 1.
Magnitude of 1, right? So once you put a hat on top of the symbol, that means you're talking about a vector of length 1. You're like, oh, you already used a vector. You already used a hat on some symbols earlier. Is that consistent with this notation? Yes, it is. If you go back and you calculate the length of the x hat, y hat, and z hat, the length of all those has been 1. All right, anyway, I'll shut up for now. So before I'll try not to go over time in here, guys. My apologies.